Good morning, students. In the first session, we have discussed what are Fresnel's of period zones, why they are called so, and how we can show that radii of period zones are proportional to square root of natural numbers. In this second session, I will explain rectilinear propagation of light based on wave theory of light. This is very important concept. It can be asked for 5 or 8 marks. What is rectilinear propagation of light? We know that light exhibits dual nature. That means sometimes it exhibits particle nature and sometimes wave nature. Rectilinear propagation of light means it is particle nature of light. That is, light travels in straight lines. To prove this concept by using wave theory, let us consider a plane wavefront ABCD of monochromatic light of wavelength lambda. This wavefront is divided into a number of off-period zones called Fresnel's off-period zones. Already we have discussed this in session 1. The secondary waves from these off-period zones will pass through the point P. So here in this diagram we can see that we have considered a point P at certain distance from the midpoint O. It is also called pole of the wavefront. At point P, the secondary waves from these off-period zones pass through the point after a certain time. As the order of the zones increases, that means as we proceed to first zone, second, third, fourth, etc., the amplitude of the wave at this point also decreases. See here, we have considered the amplitudes of the waves from the first zone, second zone, third zone, etc. be R1, R2, R3, etc. The amplitudes goes on decreasing as we go to higher order zones. We let R1, R2, R3, etc. represents amplitude of the waves at P due to the secondary waves from the first, second, third, etc. half period zones respectively. We have considered the amplitudes of these zones as R1, R2, R3, etc. Already we know that the path difference between any two consecutive off-period zones is lambda by 2, or phase difference between any two consecutive zones is pi radian. Hence, the waves from two consecutive zones will reach the point P in opposite phase. This is very important point. See here in this diagram we have shown that R1 and R2 are exactly opposite, whereas R2 and R3 are exactly opposite. What is the reason for this is explained in this point. Because as the path difference between consecutive zones is lambda by 2 or phase difference between consecutive zones is pi radian, the waves from two consecutive zones will reach the point P in opposite phase. This is the reason why we have taken the amplitudes at P in opposite direction. The amplitude of vibration at P due to any one zone can be taken to be equal to average of the amplitude due to the zones preceding and succeeding. This is very important point. I will explain once again. The amplitude of vibration at P due to any one zone can be taken to be equal to average or mean of the amplitudes due to the zones preceding and succeeding. ಅಂದ್ರೆ ನೋಡಿ ಈಗ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ನನಗೆ R2 amplitude of the wave P ಹತ್ರ ಡ್ಯೂ ಟು ಸೆಕೆಂಡ್ ಝೋನ್ ಬೇಕು ಅನ್ಕೊಳ್ಳೋಣ. R2 ಬೇಕಾದ್ರೆ ಮೀನ್ ಆಫ್ ಆವರೇಜ್ ಆಫ್ ಅದರ ಹಿಂದೆ ಮತ್ತು ಮುಂದೆ ಇರುವಂತ ಆಂಪ್ಲಿಟ್ಯೂಡ್ಸ್. ಅದರ ಹಿಂದೆ ಅಂದ್ರೆ R1, ಅದರ ಮುಂದೆ ಇರೋದು R3. ಈ R1 ಮತ್ತೆ R3 ಎರಡನ್ನ ನಾವು ಮೀನ್ ತಗೊಂಡಾಗ ದಟ್ ಗಿವ್ಸ್ R2 ಆಂಪ್ಲಿಟ್ಯೂಡ್ ಆಫ್ ದ ವೇವ್ ಅಟ್ P ಡ್ಯೂ ಟು ಸೆಕೆಂಡ್ ಝೋನ್. ಅದನ್ನೇ ನಾನೀಗ ಇಲ್ಲಿ ಬರ್ದಿದ್ದೀನಿ. See here we can write R2 as mean of the preceding, that is R1, and succeeding, that is R3, divided by 2. That means we have taken the mean of these two amplitudes, preceding and succeeding amplitudes. Similarly, we can write R3 as the preceding is R2 and the succeeding is R4. R2 plus R4 by 2. Is it not? Now, the resultant amplitude at P due to the entire wavefront can be written as R equals R1 minus R2 plus R3 minus R4 etc. up to Rn. Why we have taken minus sign here? Because when we compare R1 and R2, R2 is exactly opposite to R1. That's why we have taken minus sign for this R2. Similarly, R4 is opposite to R3. That's why minus sign is taken for R4 and so on. Now, using the expression for R2, R4 in the expression for resultant amplitude at P, we can write capital R is equal to R1 can be written as R1 by 2 plus R1 by 2 because we know that half plus half is equal to 1. R1 can be written as R1 by 2 plus R1 by 2 and minus R2. Next, R3 can be written as R3 by 2 plus R3 by 2. Similarly, minus R4 plus R5 can be written as R5 by 2 plus R5 by 2, etc. So on. For these three terms, we have taken bracket. They are written inside parentheses. Why we have considered these terms, these three terms? Because, see, if you substitute for R2, that is, R2 is given by R1 plus R3 by 2. When we substitute this R2 value, then the term inside this parenthesis will be 0. Similarly, if you substitute for R4, then the term inside this bracket or parenthesis will be 0 and so on. That means except R1 by 2, the entire terms will become 0. Therefore, we can write it as R is equal to R1 by 2 plus etc. Rn by 2. For nth zone, we can write Rn by 2 if n is odd. Suppose if n is even, then the resultant amplitude at R is equal to R1 by 2 plus Rn minus 1 by 2 minus Rn if n is even. Different expression for odd and even. But for large zones, when we go to higher number of zones, large number of zones, then the value of Rn as well as Rn minus 1 will be approximately 0. For large zones, higher zones, these two values Rn as well as Rn minus 1 will be 0, approximately equal to 0. Therefore, the expression for resultant amplitude at P due to the entire wavefront, even if the n is odd or even, the expression is R is equal to R1 by 2. That means we can notice here the resultant amplitude at P due to the entire wavefront is given by only half of the amplitude due to the first stop period zone. Notice here R1 is nothing but amplitude due to first stop period zone. Half of the amplitude due to first stop period zone. Thus, the amplitude at any point P in front of a large plane wavefront is equal to half of the amplitude due to the first stop period zone. It is only equal to half of the amplitude due to the first stop period zone. We know that intensity is directly proportional to square of the amplitude. Therefore, resultant intensity at P is proportional to square of the amplitude. If you square this term, then you will get R1 square by 4. I is proportional to R1 square by 4. The intensity due to first stop period zone is R1 square by 2. That means only 1 by 4 times the intensity due to the first stop period zone. Notice here the intensity at P due to the entire wavefront is just equal to 1 by 4 times the intensity due to first stop period zone. Hence, the intensity at any point due to a plane wavefront is only 1/4 of the intensity due to the first stop period zone. Suppose an obstacle is placed in front of the wavefront so as to cut off the first stop period zone. You have to place an opaque body such that it will cover the first stop period zone. Then the intensity at P is given by R2 square by 4. If the first stop period zone is covered, then the intensity at P due to the entire wavefront without first stop period zone is 1 by 4 times the intensity due to second half period zone. If an obstacle is placed in front of the wavefront so as to cut off the first 50 half period zones, notice here, for entire zone it will be 1 by 4 times intensity due to first zone. For entire zone without first half period, it will be 1 by 4 times intensity due to second zone. For without first zone, it will be 1 by 4 times second zone. Similarly, without 50 zones, you have to take one extra. For C, for the intensity without first zone, it will be R2 square, that is the intensity due to second zone, by 4. Similarly, intensity at P without first 50 half period zones, it will be 51 square. That means intensity due to the 51 half period zones, 51th half period zone divided by 4, which is almost 0, practically 0. From this explanation, we can conclude that light does not bend over obstacles whose dimensions are large in comparison with the wavelength of light. This is very important point. Light can bend round obstacles up to where? Up to the size of the obstacle is comparable to wavelength of light. If the size of the obstacle is large, it cannot be compared with the wavelength of light. Light does not bend. That means light travels in straight lines. If it bends, then it won't. Intensity will remain same. Since the intensity almost becomes zero, that means light does not travel. It does not bend. That means it travels in straight lines. This property is called rectilinear propagation of light. According to Fresnel, the bending of light is seen even if the dimension of obstacle is comparable to wavelength of light. See here, bending of light is seen even if the dimension of obstacle is comparable to wavelength of light, or if the dimension of object is less than the wavelength of light. But if the dimension of object is more than the wavelength of light, then there is no bending of light. This explains how Fresnel explained rectilinear propagation of light, which is approximately. Why we have used this word approximately means if they are comparable, then light undergoes bending. When the size of the obstacle is not comparable to wavelength, then only we can say that light does not bend, it travels in straight line. That's why we have used this word approximately. This is the explanation for rectilinear propagation of light by using Huygens wave theory of light. I hope all of you can explain this concept, very important topic. In next, zone plate, how we can construct zone plate and theory of zone plate and how we can compare zone plate and convex lens. It will be discussed in next session. Okay.